Hello everyone, today we're going to talk a little bit about the periodic trends. Our modern periodic table consists of periods, which are the rows that go horizontally across, and groups, or families, the columns that go up and down. Our elements are ordered by increasing atomic number. This is in contrast to one of the earlier periodic tables by Dmitry Mendeleev, which was organized by atomic mass. A periodic trend is a pattern in a property that elements have that repeats or is in some other form predictable. Trends can be for either physical properties or chemical properties. Some important trends that you should know include: you should be able to determine the number of valence electrons for an element that is in the main group by looking at where it is placed on the periodic table. Conveniently, the number of valence electrons equals the number that is in the ones place of the group number. Reminder that this only works for main group elements, aka those of the S and P blocks. The transition metals in the D block and the rare earth metals of the F block do not work for this. Another thing you should be able to do is identify common charges. Starting at group 1 and only counting main group elements once again, we have a +1 charge. Group 2 is +2. Skipping the transition metals to go to group 13, which is the next column of the main groups, we have +3. At group 13, we have plus or -4. You'll notice that it is transitioning between signs here. Then at group 15, we have -3. At group 16 is -2. Group 17 is -1. And at group 18, we are at 0. The noble gases do not usually have a charge. Another important thing you should know is atomic radius. The atomic radius is a measure of the size of an atom. Specifically, the way we measure this is we measure from the nucleus to wherever the valence electrons are. The atomic radius will be very small. Generally, most are on the level of angstroms, which are around 10 to the -10th meters. The trend on the periodic table is that as you go down a family, the atomic radius grows. Meanwhile, as you go across a period heading from left to right, the atomic radius will shrink. You should also know the trend for ionization energy. Ionization energy is the energy required to remove an electron from an atom. As you go down a family, the ionization energy will shrink. As you go across a period, ionization energy will grow. You should also know about electronegativity. Electronegativity is the ability of an atom that is participating in a bond to attract electrons towards itself. You will notice when you see electronegativity values listed, the noble gases will not be included. And so the trends we'll talk about here generally ignore the noble gases. As you go down a family, electronegativity will shrink. As you go across a period, electronegativity will grow. Electron affinity is the energy change that occurs when an electron is added to an atom. For most elements, this will be exothermic, a large negative number. As you go down a family, less and less energy will be released. The electron affinity will shrink. In this particular case, it is becoming a less negative number. As you go across a period, more energy will generally be released. The electron affinity grows. Once again, the exception here would be the noble gases. They are the only family on the periodic table who does not have an exothermic electron affinity. Instead, theirs is endothermic. It requires energy and is positive. However, the trend about going down a family still applies to them. Each of the 4 properties, atomic radius, electronegativity, ionization energy, and electron affinity, have the trends they do because of a similar reason. That cause is the Coulombic force that is present within an atom. So we should discuss what Coulombic force is. The Coulombic force is an attractive force between charged particles. The Coulombic force between 2 particles will grow if either one or both of the charges increases in size, and or B, the distance between the charges shrinks. Think of magnets. It has a very similar force with a slightly different name, but generally the same kind of traits. If the magnets are stronger, they'll be more attracted to each other, or if the magnets are closer, they'll be more attracted. Charged particles behave in a similar way. So, if we were to try to explain the trends that we have already seen, we should use Coulomb's law. Why does ionization energy grow as you go across a period? Let us consider what is happening as you go across a period. The radius is shrinking, but it's not by very much. So using the explanation of distance being smaller could help, but probably is not the main cause. The other thing that's happening within the atom as we go across a period is that the number of protons and electrons is growing, which means the charge, specifically the nuclear charge due to the protons, is growing. So if we wanted to explain why the ionization energy grows as you go across a period, since the number of protons in the nucleus, aka our nuclear charge, is growing as we go across a period. This will lead to an increase in the Coulombic force, making valence electrons harder to take away. Let's look at a second example, this time talking about going down a family. Let's focus on electronegativity. Why does electronegativity shrink as you go down a family? Let's consider what's happening at the atomic structure and then which aspect of Coulomb's law we can use to explain it. When we're dealing with atomic structure for this, the radius gets bigger as you go down a family. The number of protons also gets larger, and by quite a significant amount. However, if we tried to use the explanation we used previously of a stronger nuclear charge leads to a stronger electronegativity, we get the wrong answer here. Electronegativity is supposed to shrink. So the number of protons somehow must not factor in here. The radius must be the explanation. The atomic radius gets larger as you go down a family because the number of electrons is getting larger, so they simply need more room. This larger radius means the distance between the nucleus and the valence or bonding electrons is much larger, which results in less Coulombic force, and therefore you don't hold on to those electrons as well. Let's look at another example question that specifically relies on our knowledge of the trends and Coulomb's law to explain a relationship between two specific elements. Neon has a higher first ionization energy than fluorine. Use the principles from Coulomb's law and atomic structure to explain this phenomenon. So let's consider what is going on in neon and fluorine atoms. Neon has 10 proteins in its nucleus, meanwhile fluorine only has 9. This means that neon has a higher nuclear charge than fluorine. They are also in the same period, so we won't have a drastically changing radius here impacting anything. We know that as the charge increases, the force of attraction should increase. So we string it together to construct our explanation. Since neon has a greater nuclear charge than fluorine, neon's valence electrons experience a much greater force of attraction to the nucleus. More energy will now be required in order to remove an electron from neon, and thus neon has a greater first ionization energy. You'll notice I said first ionization energy on the previous slides. The first ionization energy is the definition for ionization energy you are used to, where it is the energy required to remove one single electron from a neutral atom, often given the general form of some element X has energy applied to it and becomes a +1 cation of X, and an electron is kicked out. The second ionization energy then would be the energy required to remove a second electron from the +1 cation created in the previous step of the element, where the general form of the +1 cation has energy applied to it to yield the +2 cation and an electron. You can continue and go on to do third, fourth, fifth, etc. ionization energies until you've run out of electrons to remove. Each time you remove one, the energy will. You should be able to analyze data regarding successive ionization energies. Each successive ionization will require a greater energy in order to occur than the previous one did. This is because as you remove each electron, the hold that the nucleus has on the remaining electrons gets stronger and stronger. The effective nuclear charge felt grows because there are fewer electrons there to shield. You'll also notice there are usually large gaps between certain energy levels. For example, in the data shown above, there appears to be a large gap between the third and fourth ionization energies. This is because these must be coming from different orbitals. So, if we look at this, to which family does the element whose ionizations are shown above likely belong? So while I do see an increase between the first and the second to the third, and the third to the fourth, and the fourth to the fifth, there is an unusually large gap between the third and the fourth ionization energies. of almost 8,000 or more. This implies that the third one was the final valence electron that was removed. Therefore, this must be a member of a family that has 3 valence electrons. Therefore, this is likely a member of group 13, boron's family. Speaking of, what we previously discussed is related to the last trend that you should be aware of. What happens to the radii of an element when it becomes its ion form? The general trend is that cations will shrink while anions grow. When a cation is formed, electrons are removed. This means that less electrons are sharing the same number of protons. Thus, the effective nuclear charge will go up due to the decrease in shielding. Conversely, when an anion is formed, electrons are being added. This means that more electrons are sharing the same nuclear charge that was present. Therefore, the effective nuclear charge felt by electrons, especially those in the valence sets, is going to be much less due to that increase in shielding. This is all that we will be covering regarding periodic trends.